Hello students, again in dynamics class we are right now in kinetics. We first cover force and acceleration. Today we are gonna go through the work and energy, and we will cover for this week, and we will go through the impact and then also everything till the end of kinetics subject is gonna be done. The first thing is the work of a force, motion of a particle using the concept of work and energy. As it is representing here, let's say we have a fixed point of O, and then a particle in the, again, a curved path. We have the particle here, and with the time it jumps to the here with the given force. So we know that from our physics class, Fx is gonna give us the energy, right? So in the vectoral form, this is, let's say we have an r and r prime. From our vector calculus, we know that this dr, the distance between this point to this point in vector representation, is dr is equal to r prime minus r, as it is here, and then force is gonna act on it, but we need to, what we need to do, we need to project on the same direction, right? If we want to project, because it is, if it is vectoral form, is gonna be f in the vectoral form dot product with dr, which is r also in vectoral form, or delta r, let's say, and r is in the form, and we know that this dot product is f r cosine theta, as you remember in your calculus, vector calculus. So in the infinitesimal line, infinitesimal portion, let's say we have a dr, so and this change is ds, like the path in the magnitude is ds. So we can represent it as this concept, the infinitesimal change of energy is equal to the force acting on it multiplied by cosine theta, which is gonna be the project on the path of ds. So f ds cosine theta is gonna give us the infinitesimal change in this s direction, or like whatever the tangent of this path. And we need to remember that 1 joule is 1 Newton meter, because as you see, force is Newton, and our delta r is distance, which is meter, or whatever, like centimeter or what. So it's gonna be Newton meter. Newton multiplied meter is gonna give us joule. We are representing the energy as joule. So this result may be interpreted in one of the two ways, either as the product of f and the component of displacement ds cosine theta is the same thing, right? If you do that product, which is I multiplied by I, j multiplied by j, k multiplied by k in Cartesian coordinate, like with the coefficients. Or you need to just, like, if you know the ds, which is dr magnitude, if you change it in the magnitude of ds, then if you know between this dr and f angle, you need to just multiply by cosine theta with ds, multiply f is going to give us the energy. Or as the product of ds and the component of force f cosine theta in the direction of displacement, like either like you are gonna bring this dr onto f, or f to the dr is gonna be the same direction in order to multiply, because F dot dr is dot product is, as I said, is I x direction multiplied by x direction. If you multiply x direction multiplied by y direction component is gonna give us 0 because I dot product with j or I dot product with k is gonna be 0. Because y is normal to each other, they have 90 degrees between. So if you multiply cosine 90 is 0, so ijk, if you multiply each other, is gonna be 0. This is the reminder of this vector calculus which you guys previously took. If we calculate the work with variable forces, which means your f function is given by the dr. With dr is f is changing, as you see, f cosine theta is changing by the distances. Okay, so that means your s is depends on the distance. So what we need to do, we need to take the integral, because if we have this curve, under this curve is gonna give us the energy. So in the integral form is the change of energy is equal to from R1 to R2 or S1 to S2 F multiply dot product dr. This is dot product. Let's take the in the magnitude form S1 to S2 integral F cosine theta ds is gonna give us the change of energy from one point to another point. Sometimes this relation may be obtained by using experimental data to plot a graph of f cosine theta versus s. Then the area under this graph bounded by S1 and S2 represent the total work in figure that shows. But here is curve, so it's hard to calculate under area. If it has a rectangular shape, and then if we know this height, we can divide it into one area and the second area, so we can just take the area and then we can calculate the energy without taking any integral calculations. Now let's go through work of a constant force moving along a straight line. So our force is constant, it's not depend on anymore the distance change. Okay, so as we know that the change of energy is equal to R1 to R2 F dot dr, or in the magnitude form S1 S2 F cosine theta ds. Let's take this guy, okay, and then we know that F is constant because it's given here, constant force. It's not depend on ds anymore, and cosine theta as usual is constant. So let's take these guys out of the integral, and then we will just leave it ds from S1 to S2, which we take the, let's say 1 ds, if we take the integral is going to be s from S1 to S2, so it's going to be S2 minus S1. So the change of energy is F multiplied by cosine theta the delta S, which is change of the path. So as you see, the force is constant. Force multiplied by cosine theta is going to be constant from S1 to S2. It doesn't change anymore. So what do we need to do? Just need to multiply each other. That's it. Like it's the under this area, right? This curve. If you multiply from S1 S2, let's say it's an S multiplied by delta S. Delta S multiplied by FC cosine theta is gonna give us this rectangular area, which is giving us an energy change. So also here, let's see here. So our path is straight. and if our force with an angle, we need to multiply by cosine theta in order to project our the force into this direction. Okay, so we can multiply, because if we take sine cosine fc sine theta is gonna bring in this direction. Let's say we have because the path doesn't give anything here, so fc sine theta multiplied by it doesn't change in the y direction, so it's gonna be 0. So there is no energy concept in this y direction, so we just neglect, we just bring this f constant component of in the s path. If we see the work of a weight, we know that from our gravitational acceleration is on the y direction, or like the z direction, whatever it's called, but in this plane is x, z, and y, so it's gonna be y direction, so it's gonna be minus g right here, or like the acceleration is on the downward. So our weight is this magnitude and minus j direction, and if we have this force acting on it, which is mg, we know that is an mg. If we multiply this one with a dr, which is in Cartesian form, is the change of x direction, I, which is x direction unit vector, plus y direction change multiplied by j direction, y direction unit vector, plus z direction change in z direction multiplied by z direction unit vector. So if we make the force or weight dot product with dr, is gonna be minus w, which is the mg in j direction, multiplied by this dr dxi plus dyj plus dzk. So we know that from dot product, this j multiplied by I is gone 0, and j multiplied k is gonna be gone 0. So j multiplied by j is gonna be 1, so we will keep it. So w dy is gonna be our answer, and then we have minus w dy is from y1 to y2, because r1 and r2 is gonna be in this changing. So we know that x direction and z direction there is no change. Even though it changed, it doesn't matter, because it's only matter in the y direction because of this dy. So if we are gonna take, of course, w is mg, which is both of them constant. So mg y1 minus y1, y2 minus y1 is gonna give us the energy from point 1 to point 2. So it's gonna be given minus w delta y, which is basically is a potential energy, right? Potential energy, because we know that w is mg, and if we take delta y from that point to that point is gonna be h. So mgh is gonna be our potential energy, which is the same thing as representing this form of energy. If we want to calculate the work of a spring force, we know that the force of spring is Ks, as you remember from our kinematics part. Also the force and acceleration part, I gave you guys Kx or Ks because we give the ds form. So from energy from one point to second point is gonna be integral of S1 to S2, the spring force multiplied by ds, okay, which is the change in this spring. And if we want to plug this Fs force, is gonna be minus Ks, ds from S1 to S2. So in short way to say is gonna be, if we take the S ds, is gonna be k is the constant, we can take it outside as minus k, and s is gonna be s squared over 2, so it's gonna be 1 over 2 ks squared for the second one minus the first one. And then if we have the minus here, the first one, like first equilibrium point to the second equilibrium point, if you subtract, you will have the energy losing or gaining for the system. This work represents the trapezoidal area under the line Fs Ks. So of course, if K is constant, if K is not constant, it's not gonna be a linear. If K, it depends on the force acting on it or the distances, then there can be a change of parabola or something. But right now we are talking about linear systems. So it's gonna be linear increasing, so it's gonna be trapezoidal area. So we can calculate it without this formulation. Just take the area of under this curve from S1 to S2, then we can have our energy term. But the more scientifically, we need to use this form. The principle of work and energy, let's do this guy in this schematic way. Let's say we have a particle on again a path or curved path. So we have resultant force acting on this direction. We know that the components in the normal direction and then tangential direction. So if we want to calculate the tangential direction, because in the path, the tangential stuff, because we know that this radius of curvature is going to be constant, and the normal force is going to be act like a centripetal force. But in tangential direction, there's going to be energy loss or a gaining. So we need to take the total force of in tangential direction multiplied by the path change from point 1 to 2. So it's going to be ds, right? From, if we take the energy, is the total force in tangential direction to taking the integral of from S1 to S2 ds. So this is equal to mv dv from v1 to v2, which is velocity 1 to velocity v2, the mass multiplied by the velocity, and then we need to take the integral with change of velocity. How we come from this guy to this guy? Because we know that F is ma, which is ma ds. We know that from our kinematics part, ads is equal to v dv. So instead of ads, we wrote here v dv is gonna be mv dv. If we take the integral, it's gonna be 1 over 2 mv square, v2 square minus v1 square. So as you see here, 1 over 2 mv2 square minus 1 over 2 mv1 square is gonna be our change of energy, which is, we know that from here is a kinetic energy, right? From our kinetic energy from our physics class. Here is the same thing, like we know that the resultant force, if we take the resultant force here, if there is a theta, if we want to project this resultant force into the tangential force, we need to multiply by cosine theta. Sine theta is going to give us the normal direction force acting on this particle. So we go through all this form of energy, which is potential energy, kinetic energy, spring energy, right? Like the external energies acting on it. So let's keep it like spring energy and blah blah. This equation represents the principle of work and energy. We are gonna show here. We know that from the sum of the work done by all the forces acting on the particle as the particle moves from point 1 to point 2 is gonna be the total energy is gonna be the change of the path motion. So if we have the potential energy plus the spring energy is gonna be reflect to the motion of this particle. So we can say the total energy is from our kinetic energy is equal to our kinetic energy we can represent by. So this is all this blah blah. As you say, okay, let's make it like our kinetic energy T, which is 1 over 2 mv square. So T1 plus the total energy we have is gonna end up our second stage of kinetic energy. So let's say we have one particle in rest. So the kinetic energy in the first point is 0. So we have a potential energy. So you are gonna write here mgh, whatever it is. So is equal to your so here is the change, right? So here 1 over 2 mv2 square. So whatever your potential energy is gonna consume, change on potential energy is gonna exchange to the kinetic energy. So m is gonna be constant, and v2 is gonna be square root of 2gh. So you directly find your second velocity of this particle in the rest at the first stage. Then after that, if you have the potential and then if you release, it's gonna have ended up with a motion. Before we go through all the examples we are gonna solve, let's go through our steps how we are gonna approach. First of all, we are gonna draw our free body diagram at first. Like we will draw all the components of the forces acting on the body, and then if there is an inclined surface, we will show everything clear. Then we will start solving our question. Then we will apply the principle of work and energy, which is, as I show right now, T1 plus total energy change is equal to the second stage of the kinetic energy. So we will solve all our question with this principle. If the kinetic energy at the initial and final points is always positive, since it involves the speed squared, so the mass is positive, the velocity also, if it is square, is going to be positive. So this too is going to be positive. So we need to keep in mind a force doesn't work when it moves through a displacement in the direction of the force. That is already explained. And work is positive when the force component is in the same sense of direction as its displacement. Otherwise, it is negative. So we make it our force project to the path, right? If the energy is negative, so that means the work acting on it again in the negative direction, like a friction force. Okay, if we keep moving, forces that are functions of displacement, so if it is Fs, so we need to take the integral, right, must be integrated to obtain the work. Graphically, the work is equal to the area under the force displacement curve. If it is we have a triangular shape, or we can calculate the R under area, right? or trapezoid shape. The work of a weight is the product of the weight magnitude and the vertical displacements, which is, as we showed also this one, is positive when the weight moves downwards. The work of a spring is of the form 1/2 ks square, where k is the spring stiffness and s is the stretch or compression of the spring. So we show all this stuff. This is the brief introduction of this principle of work and energy. What if we have a system, like what I mean, let's say we have a boundary of a shape in this shape, and we have a particles of not once, multiple particles and different shapes. So in that case, we will take as this boundary as a system. So we are gonna say if this system has a total kinetic energy T1 plus the internal energy change U12, the total change is gonna be end of the system. Or you can take each one's the kinetic energy of this particle, which is hard if we have too much stuff, too much particles, is gonna be hard to calculate it. That's why we are taking as a system, and we are taking the first system, like how this system moves in what direction, I don't know. So in the second stage is gonna be at that S1. So you are gonna say, okay, from this guy, it has this velocity, so it's gonna be 1/2 mv squared. The total m is constant. Then the total m with the second velocity is gonna give us all the internal energy changes. Before we go through the example, the last thing, let's depict the frictional force is acting on the body. So let's say we have a block and it applies force of P, and then it has a velocity V, and from S1 it comes to S2 with a constant force and constant velocity. So in this case, we are going to say our first in kinetic energy is 1/2 mv squared. We know that there is a P is a force acting on this body, PS, from S1 to S2, which is delta S, is going to give us energy changing this direction, right? Fs. And we have a friction force. So it's going to be nu, and then the mass of this body, the normal force. So nu k multiplied by n multiplied by s is going to give us frictional force, is equal to 1/2 mv squared, which is v is going to be constant. So this guy is going to go as this guy, and ps is equal to nu and s. So s is gone. So p is nu k n, which is, it says here, if we have the force acting on it exactly the same as friction force, is going to be constant velocity in this s direction. But if p is bigger than nu k multiplied by n, then it's going to be velocity 1 and velocity 2. So changing velocity in positive direction, so there is more velocity here. If it is like this p is gonna be less than this one, if we have initial velocity, so it's gonna be v2 is gonna be smaller, so in some points it's gonna stop. So okay, again we use this our main formula, and then like solve, add all the variable like friction forces. If there is like under spring force, we will need to add. If we have potential energy we need to add over all in this side. Okay, and then we are gonna solve all these work and energy problems. Okay, let's jump to examples, and then we will be understanding better. Okay, in this question, let me turn this guy on. Okay, when S is 0.6 meter, so here is 0.6. The spring is not stretched or compressed, so it's neutral. Okay, so the force acting or energy on this spring is 0. And then 10 kilogram of this mass is attached to this spring and then release. And also this mass has this block has an 100 Newton force pulling by downward. We have the velocity of this block right now 5 meters per second. This is a smooth plane, so there is no friction. There is no zero. Okay, we ignore the friction, and we are gonna find the distance s when the block stops. So when the velocity is 0, so v2 is 0, we are gonna stop s2, right? Let's say this is s1 is 0.6, at s2 somewhere here is gonna stop. Let's draw our free body diagram. We have an inclined surface, a block, we have a force, right? And we have an mass acting on it. So in order to find our normal force, is gonna be between this angle is gonna be 30. So if we want to add this mass, mg cosine sine theta, which is in this direction, is gonna add mg sine 30, is gonna be acting like a force, and we need to add there in order to find our like our stuff. And this normal force doesn't matter because we don't have any acting on this let's say y direction, because there's no friction, so it's useless to calculate it. We just need to add this force because it's due to the mass is going down as well with the gravity. Okay, let's solve one by one our energy. So due to the force, let's say UF, due to the force, we have 100 multiplied by F multiplied by the change of S, right? From 0.6 to that point, whatever it is. So we are gonna say S2 minus 0.6 is gonna give us this UF. The second one, U weight, which is from the block's weight, is gonna give mg sine 30. So mg sine 30 again s2 to s1, which is 0.6. So m is 10, g is 9.81, sine 30 is 1 over 2. So this guy is gonna be let's say 98.1 over 2 s2 0.6. Okay, so the third one is the kinetic energy, the potential energy of the spring. So us spring energy is gonna be minus 1 over 2 k, which is the constant, spring constant is given here, 200 Newton over meter, from where again s2 minus s1, which is 0.6, but here square. So it's gonna be minus 100, because this is 200. We will solve divided into 100 S2 minus 0.6 square is gonna be our spring energy. Okay, we know this three. Then we know our main formula, which is T2 plus the total of energy from point 1 to 2 is equal to our last, right? So we know that our first, sorry, this is T1. Yeah, the first kinetic energy is 1 over 2, m is 10, and we have velocity of 5 square, plus all this one, 100 multiplied by S2 minus 0.6 plus 98 is 49.05. 49.05. Again, this guy. So instead of this 100, I will write 149.05, which is the force, and then mg, the potentials, the weight. Is a potential energies acting on it, S2 minus 0.6 plus, sorry, it's gonna be minus, due to the 1 over 2, is gonna be minus 100 S2 minus 0.6 square, right? Is equal to where T2 when the motion stops, the velocity is 0, so it's gonna be 0. 1 over 2 mv square, v is 0, so it's gonna be 0. Is a quadruple quadratic equation, so it's very easy to calculate. We are gonna open up, and then we will calculate the root of S2, which is, you will see if you make this calculation, you will see S is gonna be, S2 is gonna be 2.69 meter. So from 0.6 meter to 2 meter and 0.3 is ahead. The delta S is gonna be, so 2.03 meter. Okay. In the second example, we have a brick, 2 pounds brick is sliced down from the roof, and with 5 feet per second velocity from point A, the initial velocity is 5 feet per second, it comes till B, okay, and then the angle is 345 triangles of the roof. So it's gonna ask us to find the C, how it strike to the C, and the speed, okay, and the distance d. So first of all, let's see how it's gonna, when it comes from point A to B, what is the velocity at this point, and then we are gonna make our either work and energy, or our kinematics knowledge from projectile motion. We will calculate at c velocity and this d distance. All right. We know that for the first stage from TA, which is the beginning of kinetic energy, plus the total from point A to B energy change, is gonna be equal to point B's kinetic energy. So it's gonna be 1 over 2 mv square. M is here is 2 pound. Pound is like the weight, so we need to divide it by the gravitational acceleration, which is in British unit is gonna be 32.2. So it's gonna be 2 over 32.2 in order to find the mass of this brick. And we need to multiply the velocity, which is 5 feet per second. So we need to 5 square. And plus, as you see, it just has the velocity from the kinetic energy, we know that, and also has a potential energy. We know that mgh is gonna give us the change, right? Change of potential energy from point A to point B. So it's gonna be mgh. Mg is here 2 pound. I already write it, and then we need to multiply by the 15, which is change of elevation. So we write the potential energy change in this point A to B, and this is equal to 1 over 2 again mass of brick, which is 2 over 32.2, and VB square. What do we need to find? VB square. If we make these calculations, you can find VB is 31.48 feet per second. Okay, from A it is 5. Right now we are here and the velocity is in this direction, right? And it's gonna be 31.48. So let's go to second stage, how we are gonna act on this second stage. Our second stage is second way is from A to C, because we already have the same procedure. Instead of 15 we can make it for 30. We can add 30. We can do the same procedure. TA plus the total UA to C is equal to DC, which is 1 over 2 m is 2 over 32.2 multiplied by V, which is 5 square, is equal to, is plus the weight, which is 2, multiplied by the change of elevation is 45. 2 multiplied by 45, and we are gonna have 1 over 2 over the mass of the brick, 32.2, and velocity of C square. If you do this calculation, you will find the C velocity is 54.1 feet per second. Okay, we find the speed as C. We need to find the distance D by using our kinematics knowledge. Let's do it. Yeah, let's see. This is a tree. So, okay. Let's draw a graph. We know that at point B we have the velocity B, right? And we have a triangle 3, 4, 5. So it's gonna be 3, 4, and 5. And we have a distance D for point C. Okay, from the knowledge of horizontal line, we know that XC is equal to XB, which is the position of C, is equal to position of B plus the horizontal velocity of VB, right? Horizontal velocity of VBX, multiplied by time of flying, right, on this line. So XC, which is, let's say, is XC minus XB is D, is equal to VBX. What is VB? Is 31.48. 31.48. What do we need to multiply by? We need to multiply by 4/5, right? In order to find our horizontal, we need to multiply by 4, and the horizontal, like, is cosine theta, 4/5, and t. So just let it this one like this D, and then let's pass in the vertical position. We know that from YC is equal to YB, which is Y position of B, plus the initial velocity, which is VBY in Y direction, multiplied by time, minus 1/2 gravitational acceleration t square is gonna give us this distance from YC to YB. We know that YC is at the ground is 0 and YB is 30, right? 30 feet. Then we can say, okay, plus VBY in what direction? In the minus direction, right? So it's gonna be in the downward, is gonna be 31.48. 31.48, and it's gonna be 3/5. 3/5 t. Then it's gonna be minus 1/2. G is 32.2 t square. All right. It's again only unknown is time. We can take this is a quadratic equation. We can solve the quadratic equation, and we can calculate it. The time is 0.899 seconds. So flying time is 0.899 seconds. Then we are gonna bring here in order to calculate our d. So 31.48 multiplied by 4/5 multiplied by 0.899 is gonna give us d is gonna give us the 22.6, which is 22.6 feet. Okay. So we found our d values as well. If we have this kind of question, like if the bricks slide, and we can find the B velocity and C velocity by using the work and energy. If there's no work, there's energy, right? Because there's no force acting on it, so there's only energy. And then after that, from this B point to C point, we can use our kinematic knowledge. Then we can find the distance between from the roof edge to the crash point of C. Okay, this question is end here.